Hello and welcome to lecture 34. So today we're going to discuss volumes. This is in part of the book which is labeled Applications of Integration. So we've done this work of defining the integral, of presenting the fundamental theorem of calculus, realizing or learning from a consequence of the fundamental theorem of calculus that we can calculate these definite integrals. And the point of this section and the previous section, the area between curves, is to give you some indication of the application of this, the power of this, on some concrete type questions. And the question of volumes, of being able to calculate volumes, is perhaps more concrete than finding the area between curves. And it's a very nice application of these techniques. So I'm going to start by trying to explain the formula we're going to use in pictures, or perhaps better to say it, I'm going to explain it in terms of a metaphor. And the metaphor I'm going to use is actually extremely close to the thing we're actually going to do, extremely close to the procedure. It's going to perhaps sound a little bit strange, but it is really close to the actual mathematical procedure. And it's the first example you will see of something which I call the Riemann Sum Machine. So when we were talking about Riemann sums, I was explaining that the first purpose of this is that you see with your hands how to calculate these integrals without this powerful tool of the fundamental theorem of calculus. So that when this tool comes along, you see the impact of it, you see the power of it. The second main advantage of doing Riemann sums is that we can, with this tool, generate all the integral formulas in calculus, and that's what we're going to see here. We're going to use this tool to generate this formula for volumes. But if you look at the last two-thirds of the calculus textbook, open any collection of pages in any section, you'll see some formula for something. Multivariable calculus, we learn a new formula every lecture and a half. And all of them follow in exactly this way. And if you are someone who wants to learn math at the level of multivariable calculus, learn it in some non-trivial way, then learning this procedure is extremely valuable, because all of these things become transparent as a consequence of knowing this procedure. So it is very much worth your while getting good at this, understanding this as quickly as possible, because then everything else you will learn in more advanced calculus will relatively easily make sense to you. And the idea is always the same. The idea is simply that we have in calculus differentiable functions, and differentiable functions are locally like linear functions. And linear functions are things that we can actually calculate on. These are things we can explicitly work out. Whatever we're trying to work out, it is very simple if we have a linear function. Yeah. So we work out what it is like on a very small piece where it's close to linear. Yeah. And then we add up all the pieces. And in adding up all the pieces, we're forming a Riemann sum. Yeah? And to get an exact answer, we need to make smaller and smaller pieces and pass to the limit. That's exactly creating an integral. Yeah? So it's the same procedure in every single case for every single integral formula. It's almost an algorithm to understand these formula. And this what I'm about to present today is the very first instance. It is, please do pay attention. It is not a difficult thing, and it is also a very important thing. I want all of you to have more than a algorithmic understanding of this, and having some conception of how these formulas come about, why they are the way they are, is what you want, is stuff you want to extract from this course, particularly if you would like to study at a higher level. Okay. All right, so let's just begin. So when do we know about volumes? Well, to begin with, not too many situations. So if we have a cylinder, so something like this, where this has got radius r, and this has got height h, then we know this volume, right? It's just the base times the height. If we have some kind of a rectangular shape, and let's say this here is D, this thing here is L, and this thing here is H, then volume is H times D times L. And again, it's just base times height, or area of the base times height. Okay. But if we don't have such a simple shape, then we've got a problem. So we're going to develop a formula that allows us to find the volume of much more general shapes than this. And as I promised, we're going to do this in the context of a metaphor. So this is the metaphor. Imagine that you are a fanatic of gourmet sausages. You love gourmet sausages. You have enormous passion for this topic. You read magazines about it. You save up your money to buy gourmet sausages. This is a big part of life. I assume such a society exists. I don't really know, but I guess it must. And in this metaphor, you have saved up $10,000 to buy a particular gourmet sausage. And your gourmet sausage looks like this. From the side view, it looks like this. Because gourmet sausages, for whatever reason, have non-cylindrical shapes. Yeah. So this is what your sausage looks like. And gourmet sausages are sold by volume, not by weight, for whatever reason. Okay, so you've paid $10,000. Whoops. For this gourmet sausage, and it's meant to have 10 cubic centimeters. Okay, so after dreaming about having enough money to buy this thing, you finally go to the butcher, you buy this gourmet sausage, you bring it home, and you're looking at it, and being a sausage aficionado, you know what 10 cubic centimeters of sausage looks like, and this thing looks like it's less. Yeah? So you're very concerned. You are quite concerned that you've been cheated, that you don't have a full 10 cubic centimeters of this particular very, very fancy gourmet sausage. So you can't, in an obvious way, estimate this volume, right? You'd like to go back, you'd like to estimate the volume and make sure you've got your full 10 cubic centimeters, but it's not got a nice cylindrical shape throughout. You can't just take the base times the height. Yeah? So you're thinking about it, and you conclude that what you could do, perhaps, is just cut up the sausage into pieces. Right? Because if you cut it up into pieces, you're not going to change the volume. So you cut it up into pieces like this. Yeah. Okay, so this is how you're going to slice up the sausage. How many pieces do you have? You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You've cut it up into 12 pieces. Yeah? And every slice is like a kind of a kind of a cylindrical shape, right? Every slice kind of looks like this in some way, right? But it's not a perfect cylinder because if you look at this slice, for example, you don't have that the edges go straight down, right? But it's cylindrical-ish shape. So if we look at the side view, so what does it look like? Maybe it kind of looks like this. Right? If it was perfectly cylindrical, then these sides would go down just at just at right angles to the top, but then not. It could be something like this. Yeah? Yeah. So, nevertheless, this is somewhat like a cylindrical shape. I mean, the error away from being a cylindrical shape is just this piece here on the edge. Yeah? So, let's say the thickness, we've cut them into equal sizes. Let's say the thickness here, let's going to call it delta of x. Yeah? So this here is delta of x thickness. Yeah? And for each slice, we have some radius. So we're going to define the radius of the first slice just to be the length of this line, right? So that would be here, and this thing would be our radius, and let's call it Ri. Yeah? So we would like to approximate the volume of this slice by the fact it looks somewhat like a cylinder. And the cylinder it looks like is just a cylinder which is just created by a circle of radius Ri of depth delta of x. Yeah? And that thing would have volume just given by the base times height. So volume of this thing is close to just pi Ri squared times delta of x. And it isn't quite that because if we do that, we're not counting this extra stuff here from the edges. Yeah? But let's think about that. Well, this extra stuff from the edges, this distance is kind of like delta of x as well, right? So we have this kind of area here, which is like delta of x times delta of x, which is delta of x squared, and it's rotated around, it goes around the perimeter of the slice. Yeah? So that is going to be like the perimeter of the slice, which is 2 pi, yeah, times Ri, yeah, times this thing here, which has got area like delta of x squared. So it's this, and then let me just put in, and then the error is of order 2 pi Ri delta of x squared. So give yourself a second to convince yourself that this is correct. You know? That the only error is these little pieces, which are just like this kind of, it's contained within a circular band around the outside, where the thickness of the circular band is delta of x, and therefore the total volume of the circular band is like delta of x squared times the perimeter. Yeah? And the moral of this is not the exact formula, but just the fact that this is a lot smaller than this, right? Because delta of x is the very small thing. Yeah? So this thing is way, 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 way smaller than this, which your just visualization of this can see. Yeah? So if we looked at this from above, so from above, what do we see? Looks like this, and then we have this kind of slightly thicker extra bit here, yeah, where this is of order delta of x, yeah. So the error is indeed given by this. This is from above, and then the thickness going out from the light board is of order delta of x as well. So this is indeed the error. And again, the point is not the exact formula or even the approximate formula, just the point is that it's way, way, way smaller than the actual volume itself. So we're doing something reasonable by pretending that the volume of our slice is like the volume of the cylinder that we would get if it just had flat edges. We're doing something reasonable there. Yeah? Cool. So with this understanding, we just want to add up all of our individual slices. Yeah? So let Ri be the radius of the top of each slice. Yeah. And then total volume is approximately, I have exactly 12 of these guys. The sum from I equals 1 to 12. And then each one of these individual volumes, so it would be pi Ri squared times delta of x. Yeah? Okay, so imagine you did this. It's only 12 slices, you can cut up your thing. Each slice, you put it on the table, you take your tape measure, you record the radius of the top, yeah? And then you make the approximation that this slice has got area pretty much, volume pretty much like pi Ri squared times delta of x. You add up all these numbers, and then suppose you did that, and then you found that this will say 8.7, yeah? Where you should have something close to 10, you get 8.7. So then you're quite unhappy, and you go to the butcher with your 12 slices, and you say, this is no good. I've paid $10,000, I saved up for 6 months for this sausage, and I don't have the full volume that I've paid for. I only have 8.7 or something like that because I cut up into slices and it's a good approximation. And the butcher goes, well, you know, I don't trust your approximation here because there are these errors, and I think those errors account for the difference between your number and the actual volume. I think I sold you a genuine 10 cubic centimeter sausage, 10 cubic centimeter volume sausage. Yeah? And you're not convinced because you think the error is pretty small. Yeah? But what do? I mean, the butcher has a good argument that you haven't got an exact answer. Well, if you think about it a bit, then you come to the conclusion that if you didn't do 12 slices, but you did whatever, some larger number, the error would be much smaller. So if we just look at this slice over here, and let's blow it up. So we just took one arbitrary slice, like this. Then the error from this slice is from this stuff here, right? It's from this stuff which is being extra counted. But if we cut this slice into 4 slices, let's take all of I'm going to take all of our 12 slices and slice each one of them into 4, like this. And now we're going to, with 4 times 12, 48 slices, we're going to do the approximation of approximating each slice just by the cylinder defined by the radius of the top. Now, let's see the errors that we get. Well, we get error from this stuff that we overcount here, right? And this stuff that we overcount here. But that is a lot smaller, right? So I'm going to fill in the overcount that we get from doing this now after we cut it into 4. This overcount is a lot smaller than the overcount that we had before, which was this entire triangle. You can just see it, right? Yeah. So you imagine that this is the error we had from this slice was rotated all around like this, yeah? And now we have these thin things rotated all around like this. So these 4 cylinders, yeah, whose volume we approximate just by taking the top radius divided by the top radius squared times pi multiplied by the thickness. This is a way, way better approximation than just having the 1. Yeah? So, since we're doing this with all of our slices, we're cutting them all into 4, therefore our error is going to be dramatically reduced. Yeah? So now with 48 slices, it's a much, much more convincing argument that we have the volume. So you go back, well, you do this calculation, you find out the volume of your 48 slices, and let's say it now turns into this. Yeah? It's a little bit bigger, but it's definitely not the thing you want it to be. And you go back to the butcher and you tell him, okay, now we have 48 slices, calculated the volume of each, or approximated the volume of each one of them, and I've added them all together, and now it's this, and it's still not right. And then the butcher will go, well, you know, I'm just not going to give you back your $10,000 because it's still got errors. It's still not the exact answer, and I believe that's the difference. And then you're quite frustrated because no matter how many times you cut it up, right, there's always going to be some error. And then the butcher can always say, well, that's the reason you don't get the 10 cubic centimeters that you want. But happily, you are a calculus student, and you know how to go from this procedure of having more and more to actually having an infinite amount, right? Because what are we doing? We're going from the procedure of adding up a finite quantity of things. You know, we're cutting up into 12, then 48 individual slices. But what we'd like to do to have an accurate answer, to have a completely true answer, is not have finitely many slices, but infinitely many slices. In fact, have uncountably many infinitely slices. A slice for every x between the start and the end. Yeah? We'd like to sum together these uncountable infinity of infinitely thin slices. Yeah? And that's exactly what this concept of an integral allows us to do. The integral is this more sophisticated version of summation that allows us to sum not over finitely many things, but over uncountable infinity of things. Yeah? So, you get the butcher to agree that as you make more and more slices, the error goes down to 0. Yeah? But he's still not going to give you back your money because he says you have no idea how small the error is, even if you take 1,000 slices. But he does agree that if you had an infinitely many slices, then it would be an accurate answer. So you go back. Yeah? You go back to work. And you look at your sausage again. And you realize that for every slice, which is going to be defined from the start here, so if we slice at some point here x, then the radius of your sausage is given by some function that you can just describe. And here the metaphor gets a bit unrealistic. Suppose the radius is given by some function f of x. Yeah? So Ri is just equal to f of xi. Yeah? The radius of the slice is just given by this f of x. Yeah? Then we're going to do the procedure. Okay? Not with 12 or 48, but with an arbitrary number of slices, and then we're going to let that arbitrary number go to infinity. Yeah? Which sounds like a big deal, but it's not a big deal because we already know how to do this, because this is just doing a Riemann sum. Okay? But let's do it. All right, so how many slices? It's going to be n. Let's say this thing has got length L. Yeah? So let delta of x be L over n. Yeah? And then exactly as in the Riemann sum procedure, this is starting here at 0. L is the endpoint, so we're going to let x0 be 0. xi plus 1 equals xi plus delta of x for I is equal to 0, 1, up to n minus 1. Yeah? So in particular, this implies x n is our endpoint L. Yeah? And each individual slice is easy to calculate, right? So we're going to take the sum from I equals 1 up to n, yeah? And the area of the top of each slice is going to be pi times f of xi squared, right? Because the radius is given by f of x if we're slicing at x, yeah? So this is the top, and then times the thickness, which is delta of x, yeah? And that thing, ignore the limit for time being, that thing in these brackets here, this is exactly the expression for the sum of n slices of our sausage, yeah? Or the approximate volume of n slices of our sausage, making this approximation that we've been doing, that when we slice it, we just take the radius defined by the top slice and then approximate the volume of the slice by just this area of the top times the thickness, yeah? Which would be true again if the thing was actually had flat sides and it was a perfect cylinder, but it's almost true with a very small error in general, yeah? So this is what we do. This is what we do. And it's exactly what we've done before. We're just writing it more in the language of math, yeah? So this is the expression we had before, and again, f of xi is ri because it just happens that the profile sideways of our sausage is such that we can define the radius as a function of x, where x is how far along we've gone and taken the slice. Yeah? Cool. So this thing is this thing, yeah, and the only additional thing is that we're taking the limit as n goes to infinity. Cool. So what you should recognize here is that this is a Riemann sum. And what would be really great would be if you pause the video, look at this Riemann sum, and then try and conclude what the limit of this is. And you're going to know, of course, it's going to be an integral, but write down what the integral is. Yeah? So please do that. Spend at least 5 minutes just thinking about it, trying to look back on your notes on Riemann sums. Yeah? And then try and conclude what this thing is before you press play and then see my explanation. Okay? All right, so let's figure this out. Well, we know about Riemann sums when we're just taking the area underneath the graph. So if we just had some function g like this, right, and we're trying to find the area underneath the graph, that's how we introduce Riemann sums. We just cut things up into rectangles and then add together each one of these rectangles, right? And the height's defined by the g of xi, and the base is delta of x, and therefore we have that this integral from a to b, g of x dx, is the limit as n goes to infinity, and I'm running out of space. Put it down here, of the sum from I equals 1 up to n, g of xi delta of x. Yeah, this is what we know. And each individual expression here is just the area of an individual rectangle. This is the height and this is the base. Okay, this you should be comfortable with. Okay. Now what's different here is that we don't have g of xi, right? We have some different function, right? But it's not in any important way different. So for example, we could just define g of x to be this pi f of x squared. Yeah? And if we did that, then we could write this thing like this. And this would be just the limit as n goes to infinity, the sum I equals 1 up to n, g of xi delta of x, which is exactly the classical expression of a Riemann sum. And we know, just going through it again, what this is. This is just the integral from 0 to L, g of x dx, and then this, turning this thing back into our function, is integral from 0 to L pi f of x squared dx. Cool. So this thing is the actual volume of the gourmet sausage. There is no more any errors because we've let these slices go down to 0 and take in infinitely many of them. Yeah? There's no more argument from the butcher that this is an approximation. It's not an approximation anymore. It's the actual volume. Yeah? And what we needed was to have this function f of x that defines the radius of the slice through each sausage. Yeah? And yeah, you could make the reasonable point that why would we have such a function? Why would we know what it is? Well, I don't have an answer. Let's assume in our metaphor that the gourmet sausage has some particular function that defines this profile. And that's one of the properties of the sausage. Therefore, it's given to us. Therefore, we can just integrate it. And there we go. Yeah. So you go back to the butcher. And if this thing is less than 10, then you indeed have the right to your money back. You haven't got your full 10 cubic centimeters volume. Okay. All right. So why is this, as I promised, this procedure of breaking things up into small pieces where we understand and then summing them and then passing the limit? Well, it was based upon the fact that if we slice the sausage into this thin slice, then it looks an awful lot. Well, it's very well approximated by just taking an ordinary cylinder, which is just a circle, which is translated up or down a little bit. Just an ordinary cylinder with vertical sides. And it's not quite that, but the point we made here is that the error is very negligible. So in other words, we cut it up into a little piece where it's very manageable, where we can get a very good answer as to what the volume is. And then we just added up all these individual pieces. And to actually get the exact answer, we needed to go from having finitely many small pieces to infinitely many pieces. And that's exactly this procedure of taking the Riemann sum and passing to the limit. And that is how we get this answer. We could not have an exact answer if we didn't have this powerful tool of the integral allowing us to express something like this. Yeah? Cool. So that's why it's called applications of integration. We now can get these exact answers that were unobtainable with just a weaker notion of just adding finitely many things. And what we've actually developed here is a formula for finding the volume of revolution. We're going to talk about that later because this is just a function which is rotated around the x-axis, which is a classic way to produce many volumes. And we're going to use that particular formula going forward. But what I want to say at this point is that this is just a special case of a more general formula where we don't necessarily have a volume for which all the slices form nice, convenient circles. We can use this stuff where we have volumes that don't have such a nice profile, and that's what we're going to talk about after I raise this board. Okay, let's try and figure out how to get a more general expression for volume. So, given some object in 3D space, so it's not in the plane, it's in three-dimensional space. Let A of x be the area of the slice of object when sliced at x. Okay, I have an object rearranged. So this soccer ball is a 3D object, and let's imagine that on this table we have some axes, right? So let's put the soccer ball in the center of the axes, and then for every x, from 0 to the radius of the soccer ball, if I take a slice, I will have some thing. I will have actually a two-dimensional thing. It will be a circle in this case, And then a of x will be the area of that circle, And then that is an example of what an a of x is. But I can have any other thing, right? I could have a cake here. I could put the cake on the axis, and I can take a slice through every x, right? And then that will form a two-dimensional object. So now when I say slice, I don't mean a slice with any thickness. I mean literally a slice with 0 thickness. So this makes sense to us. So I'm going to try and draw a picture. Not so. Already a bad start. Let's try that again. Very wonky axes here. So this here is the x-axis, and we have some chunk of stuff here. This is our object. And then for every x, we slice down with two incredibly close together knives to produce something of 0 thickness, but has two-dimensional area, and that is the thing whose area we measure, and then we call that area a of x. So this is slicing here at x. So you're going to have to use, and it's a very good thing to develop, you have to use three-dimensional visualization to understand this. So if at any point this doesn't make sense, just take a three-dimensional object, draw yourself some axes, and then look at it, and convince yourself that if you slice out just a very, very thin piece, a piece of 0 thickness out of it, then it's a two-dimensional thing, which has a well-defined area. Okay, now if we do that, then the volume of the object is given by the integral from wherever we start to get non-zero slices to wherever it ends a of x, right? So as in the soccer ball case here, if we're slicing over here, we totally miss the soccer ball, there's nothing, right? So A is where we start to get something, and then B is where it ends. Now that is the same formula we had before, because what we had before was when the slices were cylindrical. Let me say that better. The slices were cylindrical because in that case I took non-zero thickness, but 0 thickness slices were in that case just circular. So previously a of x was just equal to pi times f of x squared, and that was exactly the same formula. And the formula holds true for exactly the same reason. So we took a sausage because we took a sausage which has nice cylindrical slices or circular slices because it's easier to draw pictures and whatever. But nothing in the argument really needed that. All we needed was to be able to find the area of the slice. So imagine we had some gourmet cake, completely different shape. Now let's imagine it's got some weird kind of mountainous shape. And we took this incredibly thin slice of our cake, and then we pulled it out, and then we laid it flat on some graph paper, and then we counted the number of squares it covered, right? We would have a way to estimate its area, and then we would take the volume of that thin slice of cake by just taking the area of whatever the top or the bottom, whatever we counted with our graph paper, multiplied by the thickness of our slice. Yeah? And then if we did this for all these separate little slices of our cake, even though the slices don't form these nice circular or cylindrical shapes, we could still get some estimate of the volume of the cake in this manner, and the error would be because we don't have something that has nice flat sides. Yeah? So when we just take the area of, say, the top times the thickness, that's not exactly the area. But again, the error is small compared to the overall volume of that particular thin slice of the cake. So we can take more and more and then pass the limit and then have exactly this expression. Yeah? So if you buy the metaphor, if you go along with the procedure we did just now on the first whiteboard, and that formula we came up with seems convincing to you, then running the argument, running this procedure again in your head, but now thinking about arbitrary shapes when we slice through it, this should seem reasonable too. Okay, so this is the correct formula for the volume. And this is something we're going to be able to use. And our first example is for a sphere. So, example, find the volume of a sphere of radius r. Okay, so we have a sphere prepared, but let's just draw a picture. Anyway. Okay, it's really not a good picture, but okay. So this is our sphere, a little bit flattened. And what are we going to do? So that's our 3D picture. Let's take a side view picture. So side view. So the radius is r, so the side view is going to look like this. Okay, again, not the best, but the radius is r, like this. Yeah. And we're going to be taking slices through the sphere. Yeah, let's take out the sphere we have here. Here's our sphere. We're going to take slices through the sphere like this. Yeah? So, how do we do it? Well, the slice is going to be defined by how far along we slice. So, if this here is x, yeah, we're going to produce a slice, goes up like this and down like this. Yeah? And if you're standing perfectly on the opposite side of this soccer ball, and you take this zero thickness slice, yeah, then it looks very much just like a line, right? So this is the side view. The slice will look like a line, yeah. So, but the top view of the slice, so let's put it here. So let's make the convention when I say slice, it means this zero thickness slice. And when I say slice with some thickness or thin slice, it means there's a little thickness there. Now that we've done this procedure and we believe this formula, we're always going to be talking about, almost always going to be talking about just slices with zero thickness. So the top view of the slice looks like this, right? Because we slice it through, we get a circular shape. And to understand its area, we need to know the radius of the circle. And on this picture, the radius will be what? It'll be this quantity here. I'm going to call it y of x. I think I'm going to rewrite that in a different color. So it'll be y of x. I'm not sure how clear that is. Put it here as well. There we go. That's clearer. Yeah. Again, give yourself a second to convince yourself of this. This is important. So again, with the soccer ball, we sliced it like this. Yeah? We see a circular shape. Yeah? And if we're looking at the side view, then this thing here will be the radius when we look at the top. Yeah? If you need to get something like an orange or an apple or something and just literally do it, literally do this stuff. And when you are completely happy with that this distance here is the same as this distance here, so again, this is the side view and this is the top view of the slice, yeah? Then we can go forward with this because our task is to find the area of this slice. Yeah? And what we notice is that everything lives on a circle of radius r. So this particular point here on this picture has got coordinates x, y of x, right? Because we are x along and the height is y of x. Yeah? So that means that this point x, y of x, living on the circle satisfies the equation of a circle. Yeah? So x squared plus y of x squared equals r squared, which is the radius of the circle. Yeah? Okay. Quick recap in case you have any, in case you're not happy with the equation of a circle. It's on some other video of mine, but let's do a quick recap. So if we are here on some point over the circle like this, then we create a triangle. Yeah, this is x, this thing is y, this point here is xy, and then if the circle's got radius r, then the length of the hypotenuse is r. So by Pythagoras, x squared plus y squared has to equal r squared. Right? So the equation of the circle is almost exactly the same thing as Pythagoras. Yeah? So please look at this for a second, convince yourself that this makes sense. This is why this is the equation of the circle. We just use it here. Yeah? Cool. And then we can solve. We have y of x equals the square root of x squared minus y of x squared. Ah, damn. Sorry. Totally made a nonsense there. Let's do that properly. This is the square root of r squared minus x squared. Yeah? Cool. So then we have the explicit expression for what this y is in terms of x. Yeah? Cool. So, since that's the top view of the slice, so area of the slice a of x is just pi times this quantity squared, right? And since we know what y of x is, it's this thing, it's just pi times r minus r squared minus x squared. And then we just use our formula. So volume is integral. So we're just going to integrate from doing slices going from 0 up to r because the soccer ball sphere is perfectly symmetrical, right? So if we just integrate all the slices from 0 to r and then multiply by 2, we get the entire thing. So 0 to r, and then we just put this thing here. This is our formula. We believe it. It makes sense. So it's pi times r squared minus x squared dx. And now we're in a very strong position because this stuff is just an ordinary integral, right? R is fixed, it's a fixed number. Take it to be anything you want. If you're not happy with it, take it to be 5 or 12 or whatever. Yeah? And we're just integrating this stuff. So let's pull out the 2 pi, yeah? And then we ask ourselves, what's the antiderivative of r squared minus x squared? Yeah? And then what is that? Well, we're going to have x times r squared because we differentiate with respect to x to get r squared. So it has to be x r squared and then minus x to the 3 over 3, like this. Yeah? Then we just plug in the r. And then what's that? It's going to be 2 pi. We have r to the 3 minus a third. So it's going to be times 2 r to the power 3 over 3. So that is just 4 to the 3 over 3, which might be a formula you've seen before somewhere, but now we know it. Now we know it. And with this very powerful tool of the fundamental theorem of calculus, this is quite easy to actually calculate, right? If we wanted to do this with a Riemann sum, we could actually do this because, I mean, we can do this in we can do many things with the Riemann sum, but we can do this because integrating r squared is something we've done with Riemann sums. Sorry, integrating x squared is something we've done with Riemann sums. We need this formula for the sum of I squared from I equals 1 up to whatever, yeah? And we also need a formula for integrating, no, we don't need a formula. This guy is fine. We do need a formula for integrating the x squared, yeah? But we have such a formula. So we could do this with the Riemann sum, but it's a long calculation. But now it's just one line with the fundamental theorem of calculus. So we can learn this concrete information about the volume of a sphere of radius r with this cool stuff. And obviously the volume of a sphere has been known for a long time, right? Just experimentally, the Greeks were able to figure this out. They just took spheres and dunked them in water and made some calculations and described what they saw and then came up with this, right? So it's not a new thing in any sense, or not even new in the sense in the last few hundred years. This has been known for a long time, but being able to do it so easily, that's only the last few hundred years. And it's an indication, again, of the power of the fundamental theorem of calculus. Yeah? And it's of real practical importance, because if you are the manager of a factory that is creating soccer balls, right, and you know that your soccer ball has to be a certain radius, and you know that you're going to manufacture 10,000 of them in whatever 3 weeks, then knowing the volume means you know how much compressed air you need to buy in order to pump air inside them. Yeah, there's many situations you can contrive where knowing the volume of a sphere is of real value. Yeah, so that's our first application of volumes. That's the first powerful thing we can do with them. And yeah, and it's not a hard calculation. What was hard, if anything was hard, well, okay, I agree this maybe isn't so easy if you've never seen this before, but what was hard was coming up with the actual area of the slice. And to do that, we had to visualize the situation. We had to think about what a slice looked like, you know? We had to look at the side view, take a slice, you know, and then realize that the radius of the slice will be given by this quantity with this picture. And then by Pythagoras, we know the equation of the circle, so we know the equation that this thing has to satisfy, and we could solve for x, and then that's it. So that was the hard part. The hard part was visualizing it, not doing the calculation. All right, cool. So that's our first example. Now, let's do at least one more example. So I said briefly what a volume of revolution was before. So a volume of revolution is what happens when we take some function and we rotate it around some axis. So typically, or the simplest case would be rotating something around the x-axis, right? So if we have some function defined over some interval a to b, and we rotate around an axis, imagine taking this thing and rotating it around. You're going to have this volume swept out. So we have this two-dimensional area underneath the graph, and we rotate it around. It's going to sweep out some volume. So let's try and give you an example. So if we have a constant function, so imagine around here is the x-axis, right? So we have some constant function like this, yeah? And we're going to rotate it around the x-axis. I'm going to have to go backwards because of the board, but if we rotate it around, you can see that we're going to form some kind of a cylinder shape, right? Yeah? So step back a bit. So let's imagine the axis like this, and I rotate around all the way around like this. What we have here is a cylinder. Yeah? But we can have more interesting stuff, right? So we can have a graph that has a shape, say, like this. And if we rotate this around the x-axis, then we're going to get something that does this, right? And it has a completely different shape, solid shape, yeah? Yeah. So these things have some common properties. They are what we call rotationally invariant, which means if we spin them around on their axis, then it looks the same. Yeah? I don't know how many of you have know what a lathe is. A lathe is this machine that takes a piece of wood and spins it very, very fast, and then someone takes a kind of a long chisel and then stands to the side and then grinds away at the piece of wood and cuts out pieces of it, and in that way you form this kind of whatever shape you want. So if you were going to like houses with banisters on the staircases, you have these fancy banisters sometimes, which now, I mean, they're manufactured in a factory, right? But back in the day, or in some high-end places, they're made by hand. Or bowls, for example. Bowls used to be made on a lathe, wooden bowls. Yeah. It was actually my mum's profession for many years, was a wood turner, which is exactly someone who makes things like banisters and bowls on a lathe. Yeah? And these are examples of things which are rotationally invariant. Yeah? And when you take a volume of revolution, it's something which you can create with wood on a lathe if you want to. And our task is to find the volume of these things. And it is exactly the example that we discussed before of the sausage, right? It's exactly that situation, and it's a more easy situation because we know that the slices are all circles, and the circles have their radius defined by the graph itself. So if we take a slice here, then the radius of the circle will just be given by f of x, as you can sort of hopefully see. Yeah? So this was exactly our sausage situation. So if we have a volume of revolution, for volume of revolution, the volume is given by integral from wherever we start to wherever we end. So here from a to b, pi f of x squared dx. Yeah? Yeah. So let's do a small example of this, if we can. Do we have space? Perhaps not. Yeah, erase some space. Okay, so let me say this is volume of revolution. And this is the graph of f right here. And this is the example we're going to be doing. Let f of x be the square root of x for that's the 1, and then find volume of, I'm going to abbreviate volume of revolution to V of V of R created from And we're going to have to specify which axis we rotate things around, because later we're going to do this around different axes with the same function. This one, I've done it around the x. Sometimes we're going to have a function defined on the x that we rotate around the y, and then we have to be a bit more careful. But we're just going to rotate this guy by rotating this guy around the axis, created from rotating around the x-axis. Okay, so solution. This shouldn't be too hard, right? So we have an explicit formula, we have an explicit function. Let's just draw a picture. So this is what our function looks like from 0 to 1, right? So we're going to have to slice from 0 to 1. So if we look at the side view of the volume of revolution, it's this thing that has side view like this. Yeah, and we're going to keep slicing like this. Yeah. So for any x here, then this radius here, or the radius of the slice, will be just a of x. Yeah. So all right. So we can just directly put it in the formula, right? So I was going to draw a picture of the slice and so on, but it's a volume of revolution, and we know exactly what the formula is. So let's just directly put it in the formula. So this is just going to be integral from 0 to 1, and pi f of x is just square root of x, so it's square root of x squared dx. So it's just the integral from 0 to 1. Let's take out the pi of x dx, and then that's just equal to pi 1 to 0, x squared over 2, which is just pi over 2, and that's it. Yeah? So this, without calculus, this might seem like quite a hard problem, quite difficult to find the volume of this thing. Looks, I guess, a bit like the top of a missile or something, but this is actually really easy because of this formula, which we already believe, because it's how we started this particular video lecture. Okay, so we're going to do a lot more with volumes of revolutions. It can get a lot more intricate than that, but that's how we started. All right, so have a great weekend, and see you all next week.